So we are very happy to have Ivan Dimitrov, who is a professor in Queen's University, to deliver this series of distinguished lectures in the areas of representation theory and mathematical physics. Ivan has been a professor in Queen's University since 2003. And before that, he was a Hedrick Assistant Professor at UCLA and a postdoctoral fellow at Yale University. He's an AMS Centennial Fellow, which is like a very high award in the US. He's a specialist in representation theory of the algebras and the groups. He has a number of very highly regarded works in the areas of int algebraic groups and int Lie algebras, in the areas of Lie superalgebras, Lie supergroups, and root systems. And today he's going to start his series of 5 lectures on root systems. So
Thank you. It's great to be back in this building. Just a bit on what I'm going to speak about today. I'm going to actually give a brief overview of the classical theory of root systems. There will be nothing new, but my point of view will be somewhat biased towards what will happen when I introduce the generalization next time of root system. So one thing I want to apologize, the term generalized root system is terrible because everything that goes beyond the standard definition is the generalization, and it's nothing more than an admission of total helplessness in coming up with a reasonable term. The only thing I can do about this is that instead of saying generalized, just using the abbreviation GRS for that. So I'll start just with the basic definition of a root system. Definition. A root system is a pair delta E, where E is the Euclidean space, and delta is a finite subset of E. Satisfying the following conditions. The 4 axioms. The first axiom is delta spans E. The second one is because we're in a Euclidean space, we can speak of reflections with respect to non-zero vectors. So S alpha is the reflection with respect to alpha. S alpha delta must be delta for any alpha. Here, S alpha beta reflection in the Euclidean space is given by the usual formula beta minus 2 times alpha beta over alpha. The third axiom is this is the most unnatural somehow, the one that requires most explanation. It comes from the origins of root systems in which the integers, the coefficients that appear here in the reflection must be all integers. And the fourth axiom is that if I have 2 proportional roots, then the coefficient of proportionality is just 1 over minus 1. So I don't get any proportional roots except for the opposite of them. Couple of remarks just on the definition. The first one is that if you look at these definitions, the first definition is just continuous. If delta does not span E, then I'll replace E by the span of delta. and I'll get the root system in that space. This is just not the convenience. Secondly, I did not say it here, but delta does not contain the zero factor in order to be able to write down these expressions and speak of the reflection with respect to alpha. However, it turns out that often it is convenient for delta for root systems to include zero. And when I go to the generalization, on the contrary, I'm going to assume that all root systems contain zero. And if we wanted delta to contain zero, then the modification here should have been that we exclude alpha equals zero. But that's a matter of discrimination. And the last remark is on the fourth axiom. The fourth axiom is actually not too restrictive because from the third axiom, it follows immediately that if alpha and k alpha are both in delta, then k could be, except for being plus or minus 1, it can be plus or minus half or 2. And so I'm excluding just allowing to have a root at its tower. And in terms of the combinatorial of root systems, there is no good reason for actually excluding that possibility. And I'm going to come back to that. This is where the definition, I'm not sure exactly about the exact history who put it where, but they were essentially introduced by Killing for the classification of many groups at the time. Associated with the root system is the Wow group, which is the group generated by all reflections. Because of the condition 2, where all reflections preserve the root system, this is a subgroup of the permutation group of delta, hence it's a finite. Later on, we're going to see that it is more than just one. Examples. And the level of these examples is really high school / first year linear algebra. So the first one is, the dimension of G is called the rank of delta. The rank of delta is by definition the dimension of delta. So first, if I want to consider root systems of rank 1, it has to have a root, alpha, and it cannot have any other multiples other than its opposite. And it has to have its opposite because it is the result of reflected it. So delta must be plus or minus. That's not very interesting. So this is a full classification of all root systems of rank 1. So I don't know whether we should count this as an achievement, but it is the first step. Second, if the rank of delta is 2, a little bit more work is required. However, the crucial property is here. So if I take the two roots, alpha and beta, and I look at 2 times alpha beta over alpha alpha, and 2 times beta alpha over beta beta, I get an integer, which moreover, in absolute value, is less or equal than 4. Because on top I have alpha beta squared terms, in the bottom I divide by the squares of the lengths of alpha and beta. And then considering all the possible cases for this product, I arrive at 4 possible outcomes. So I have this could be less or equal than 4. Actually, I can switch between plus and minus by no, it is a positive, yeah? Not negative. Yeah? So 0, 1, 2, 3, 4. And depending on the value of this positive integer, I have the following possible pictures. Alpha minus alpha, beta beta, beta minus beta. Where alpha and beta are orthogonal. Then I'm not relate this because I will not follow the full argument. The second one is the vertices of a regular hexagon, alpha beta, alpha plus beta, and the opposites minus alpha minus beta minus alpha plus beta, where alpha, the roots are plus minus alpha, plus minus beta, plus minus alpha plus beta, where alpha and beta are the same length, and the angle between alpha and beta is 2 pi r theta. So this is the second case. The third case is I could have alpha, beta, beta plus alpha, beta plus 2 alpha, and the opposites. So plus minus alpha, plus minus beta, plus minus alpha plus beta, plus minus beta plus 2 alpha, where alpha, the length of beta squared to square the length of alpha squared, and the angle between alpha and beta is 3 pi over 4. And there is one more example, which is you realize that you've done enough root systems and you can sketch G2 without thinking about it. So what you do is you do an A2, which is this one, the hexagon, and then within the hexagon you put you put it, I'm screwing it up now. You put a bigger hexagon. Okay, so you have the smaller hexagon here, and outside you make it bigger hexagon. And this is delta is, if I call this alpha, it is beta. Delta is plus minus alpha, plus minus beta, plus minus beta plus alpha, plus minus beta plus 2 alpha, plus minus beta plus 3 alpha, and plus minus 2 beta plus 3 alpha. Where the length of beta squared is 3 times the length of alpha squared, and the angle between alpha and beta is 150 watt in Paris. 5 hours. So these are the 4 possible cases. So in some sense, this is a whole family because there is no relationship between the lengths of alpha and beta, and these are 3 individual root systems up to this getting the length. Now, taking the first as motivation, I see that if I have 2 root systems, delta 1 sitting inside U1 and delta 2 inside E2, then I can define their product, which is usually we denoted by delta 1 product delta 2, but formally this is the this sits in the direct sum, the orthogonal direct sum of U1 and U2. These are both Euclidean spaces, so I can take some without noise, get another Euclidean space, and inside of it take just the union of delta 1 and delta 2, meaning that delta 1 sits in U1, which naturally is embedded here, and delta 2 sits in U2, which is naturally embedded here. And conversely, I say that delta decomposes if I can write delta in this way. And a system that decomposes is reducible, and a system, so any delta E decomposes uniquely as delta equals delta 1 for the delta 2, delta K, where delta I are irreducible. Now, if I want to speak of isomorphism, I did not define isomorphism over there. Is isomorphism on irreducible ones is isometry, not necessarily isometry, but up to rescaling map, linear map from one Euclidean space to the other one, which makes the scaling, in which sends one of the root systems into the other one. And isomorphism between irreducible ones is if there is an isomorphism between their components. So the point here is that if I look at these systems, the first one, is obviously, this is the product of alpha minus alpha and beta minus beta, because these are orthogonal, and it doesn't matter, there is no relation between the lengths of alpha and beta. And I don't want to distinguish between two copies of one and two systems of this form, just because one of the roots, because the relative lengths are different. It doesn't matter because we decompose. That's why I'm saying that there is more for the bosons. Most of the discussion from 1 to 4 will be about irreducible root systems. So this is this will be and so this is called A1 procession. So this is A1 procession. And it will be justified to be A1 if I had told you that this is the root system. There are one the root system. Well, hence the first of the two systems is the root system A1 procession. Then the next one here is called A2. This one is called B2. And if you are not curious, you may think of it also as T2, there is more. If you're curious, there is no C2. And this is called G2. So this is so far the classification of rank 1 and rank. I'm not going to continue with the classification of high ranks, obviously, not step by step. But I want to mention something else which is convenient. Oh, I erased my so just a remark, how can I get, as we usually teach in the algebra classes, when we introduce a structure and start giving examples, one of the first series of examples is new promote. Say you have models, how do you get more models? You have the right substance and products. So already we saw that we can take products of root systems to get root systems, and you can have subsystems. So if W is the subspace of E, I can intersect W with G, then delta intersected with W, just the roots that live in this subspace, they form a root system. Now, if I have to be careful, they do not form a root system necessarily in W, because W may intersect badly. They form a root system in the span of delta. Is a subset. So we can, so for example, in the right two, there aren't many subsystems, because if I consider a subspace, it would be a 4 dimension. Then it would be a dimension 1 and all root systems of rank 1 and A1. So I cannot illustrate two of this. One thing that is missing is there is no notion of quotient. I cannot take a quotient of the roots in a natural way and show roots. So, okay. Now, because of this observation, I see that statement. So here is a statement, proposition. We're already in a position to prove some statements about root systems. Let alpha and beta be roots. Then, if alpha beta make an absolute angle, then alpha plus beta is root. If alpha and beta make an acute angle, then alpha minus beta is root. And if alpha and beta are orthogonal, then alpha plus beta is the root. You can only if alpha minus beta is root. This is not a difficult statement to prove. For example, the last part falls from the invariance, simply because these two are just images of one another under the reflection with respect to me. These two statements, which are equivalent, may require a little bit of more work, but they're not very difficult. My point is that I don't really need to prove this in a very special way. Instead, I can look at my pictures and say, okay, alpha and beta are in delta. So I can take W to the span of alpha. Right? And everything that I'm discussing here happens is about the system delta intersecting W in the span of delta.
And in the proposition, alpha is different from plus minus beta.
No. If it is plus beta, then thank you. Here is a place where it is convenient to assume 0 is. I told you that I'll be struggling with this convention that 0 is not a root. And I would rather assume that 0 is a root, being careful in the definition not to use 0 when it's not appropriate. So, for example, in the definition of the vial group, I should say no 0 alpha, but these are the opposites. So actually, I want to be allowing alpha and beta to be proportional in the proposition, but just allowing 0. So my point was that if I'm looking at this statement, it is happening only in this rank 2 system. And I've told you what rank 2 systems are, right? These are the 4 pictures and the one missing already. And now I can just look at these pictures and see, does it work? So take 2 rules here, for example. Take this root and this root. They make a triangle. What is the difference? The difference is this root. Is this a root? Yeah, it is a root. And just spending 3 minutes on the pictures, I can actually verify these properties, and it's proof. I don't need to do it. That's just the point that I want. Another statement that comes from the same argument, strings. So suppose I have 2 roots alpha and beta. No, it's too long. And then I consider all the string of alpha string to beta. So all things on the form beta plus k alpha being z, and intersect this with the other. So I'm asking which roots in this string are root. And the claim is that then this is actually an uninterrupted string. It starts at beta minus s alpha, beta minus s plus minus s minus 1 alpha, and keeps going up to beta plus 2 alpha. For some s and t. So I cannot jump. I start here at beta. I have beta plus alpha, here beta plus 2 alpha, beta plus 3 alpha. I cannot, so here somewhere is alpha, here is beta. I'm claiming that I cannot jump and have beta plus alpha and beta plus 2 alpha, but not beta plus 2 alpha. I'm sorry, beta plus alpha and beta plus 3 alpha, but not beta plus 2 alpha. And again, this all happens in a rank 2 system, and I can go and look at my pictures and see that there is no problem. All of them are strings, and here I will sketch again the G2 system. So this is my alpha, this is my beta. So I see that, for example, a beta string, this is a beta string, this is a beta string, this alone is a beta string. And again, I have this is a beta string here, here, and here. And alpha strings are minus alpha 0 alpha, then I have an alpha string of length 4, and then I have an alpha string of length. So actually, looking at the picture, I can say more. The alpha strings to beta are at most of length 4, and I can say exactly when they are of length 4. So statements like this are just statements about rank 2s.
Is there an interesting generating function of these strings? Like we see 4 strings of length 2, 1 of length 4. Is there anything interesting about 2 strings of length 1?
We haven't thought about this. It should be known because these are essentially this is the decomposition with respect to Levi. So you take so it appears more naturally. You think of the strings as eigenspaces that are more tall, not flat. but I'm not prepared to answer the question. So, so what is the next thing I want to say? The last thing about the strings is, moreover, the mark S alpha reverses all alpha strings. So what this means is here is my S alpha. S alpha. S alpha is the reflection, and I see that actually the alpha strings are, if I look at how S alpha acts, this reflection is reverses all alpha strings. And same is true for beta. So yeah. So the next important notion related to root system is the notion of basis. So definition, subset sigma of delta is a base of delta if first it is a basis if, and secondly, for any beta in delta, I can write it now because sigma is a basis. I can write beta as a combination of elements of the base. This, right? Given the way. But then all C alpha are non-negative integers, or all C alpha are non-positive integers. So it is not just a basis of the vector space, but it is actually the whole root system is contained in the lattice generated by this base, and moreover, it is generated in the two opposite columns generated. Which brings us to this was game one. So if I have a base, then I can define delta cross of sigma as clearly all the roots that are with non-negative. Beta equals some C alpha alpha, alpha is sigma, C alpha non-negative integers, and delta minus is in a similar way. I could have written the same formula, but since from the definition we could see that delta is symmetrical about the origin, then the ones that are written with negative coefficients are exactly the opposites of the ones that are which brings me to the notion of a positive system. So here comes an absolute definition of a positive system. A subset of delta plus is a positive, a subset of delta, I apologize, is a positive system if it satisfies three conditions. First, it is together with its opposite, it gives a partition of delta. So P union minus P is delta. P intersection minus P is zero vector, because I decided that zero is the root, so now zero will be there. And if it is closed on the addition, when we speak of closed on the addition, because adding two roots does not necessarily give me a root. I mean, look at these examples. I have alpha and I have this root. There's some will be somewhere here. It's no longer. But if it is a root, I want it to be. So formula P plus P, as long as it is a root, it's still P. This is what positive system is. And clearly, delta plus is an example of positive. Example, delta plus of sigma is a positive system. I have not claimed here that there is a base here. I haven't proved that there is a base. But if there is a base, delta plus with respect to this base would be a positive. And there is a third notion that is related to this. It is just using a hyperplane. So if I think gamma to be an element of phi, assuming that the orthogonal, the hyperplane orthogonal to gamma contains only zero among the vectors, then and I denote this hyperplane by H gamma. Then the hyperplane divides space into two parts, and one of them is positive, the other one is negative. So P plus of gamma, or delta plus of gamma, is all alpha in delta such that alpha gamma is positive, is a positive. Obviously. Finish. So this is that's the definition of positive system is it provides a partition of the roots which is called from addition. And here are two examples, not difficult, but actually it requires a little bit of proof. Is the following statement that theorem P in delta is a positive system. If and only P is delta plus of sigma, if and only P is delta plus so this is saying that all positive systems are exactly the positive systems coming from bases and the positive systems coming from hyperplanes. Moreover, this the bijection, the first one is a bijection of positive systems to bases. Of course, it is not bijection between positive systems and hyperplanes, but it is bijection between positive systems and vacuum chambers. And in particular, this theorem also, in the process of proving it, we prove that every positive system contains. So from here, you read that P contains the base. So this proves the existence of bases, because positive systems exist because of that is the construction of positive system. Then it is the positive system of the base of base.
And the base is the set of indecomposable roots in the positive system.
Indecomposable meaning take two elements here, try to write them as sum of two elements in the same set. If you cannot, it's decomposable, and the ones that are decomposable are exactly the base. All these are very elementary.
So I wanted to comment that over here, your delta contains 0, but in this definition, your delta doesn't contain 0.
It does.
It's a 0.
I said 0. It's not that.
It's not empty. I missed it.
Yeah, which is just lucky for me. I may actually break this convention, and sometimes. So check whether, but yeah, I did it. Okay. I want to see how the Van group, how reflections act on bases. So suppose now that I have so let's say let alpha be a simple group. Then I want to consider a delta plus the delta plus related to this symbol. So two remarks. First is S alpha of sigma is a base of is a base of delta corresponding to S alpha of delta. So in this sentence, there are several claims. So the first claim is that if I take delta plus, reflect all roots, this is still a positive system. And this positive system has a base. This base is exactly the base that is just the reflection of all the elements. It's very simple. The only thing that is interesting here is what is S alpha of delta. And S alpha of delta plus is actually just, it differs from delta plus very little. It differs just in one word named alpha. You draw away alpha, and instead you turn minus alpha. And the proof is obvious, because if I take beta in delta plus, beta is the sum of, so this is the sum of C alpha prime alpha, sorry, C theta prime theta for theta in sigma, right? So I'm going to separate here alpha, so this is C alpha prime alpha plus some theta not equal to alpha, C theta prime theta, and these are for primes, theta, C theta theta. And now, if I reflect these, I see that S alpha beta equals minus C alpha alpha, because S alpha alpha is plus some theta not equal to alpha, C theta theta minus 2 theta alpha over alpha alpha. And now, if I look at this, unless all C theta is 0, I'm going to have a positive coefficient here. If I have one positive coefficient, all coefficients must be positive. So if I had a positive coefficient, meaning that theta is not beta, sorry, if I had a positive coefficient, which means beta is not alpha, S alpha beta is still positive. So it keeps all positives positive, and I know that S alpha is minus alpha, hence, so for any beta not equal to alpha beta in delta plus implies S alpha beta is delta plus, and S alpha is minus alpha at least in delta. So just which proves that the vowel group, so if we take this, the vowel group acts transitively, and in fact simply transitively, on the set of positive roots. So if I take any two sets of positive roots, I can go from one to the other, applying just reflections. And every step I apply a simple reflection with respect to the respective group. And then if a vowel group element keeps the positive roots, it's the identity. So this describes very well the vowel group as the action of the vowel group on the chambers. On the vowel chambers. And as a last corollary of this, that requires actually setting up the correct notation, not as much proving something very difficult. Is the fact that W, which we define as generated by all reflections with respect to roots, now, in fact, it is generated by all reflections with respect to simple roots. And in this presentation, it is Coxeter group. Coxeter group meaning that it is S alpha with the conditions S alpha S beta to the power M alpha beta equal the identity. And here M alpha beta. I'm going to go back and go to my rank 2. So the rank 2 classification, I have this alpha and beta, A1, A1, and I want to associate to this the graph alpha beta with no connection. Right. I get the A2, which was alpha and beta, and alpha and beta are now base. You can see that in what I have erased, except for G2, always I use the alpha and beta that I used, always formed a base, a basis for base for the root system. And for A2 discrete arrays, they are the same length and are denoted in this way. For B2, alpha and beta are like this. And I'm going to denote them. So in literary, they are usually denoted this way. Alpha, beta is the wrong one, so they are not this way. Gurdana prefers the notation 1, 2, and I really don't mind either way. So, and in G2 here, I see again that I have alpha and beta. In theory, it would be 3 links. Gurdana will try to one. Right. And the numbers, notice the 2, 3, and the missing 1, 1 here are just the proportion of the squares of the lengths. In this case, and in this case, so this is what happens. And now if I write down the M alpha beta is 1 if they are not linked. Sorry, F alpha beta is 1 if alpha equals beta, 2 if alpha and beta are not linked. 3 if they are linked by 1. 4 and 6. Well, yeah. If it is 1, 2, it is 4, and if it's 1, 3, it is 6. So this is the documentation of the course. So I have about 5-7 minutes.
Or even more, even more. We started late, so 10 minutes.
Yeah, great.
Okay.
So I'm going to continue this, just continuing the review. And express so one can derive a lot of further properties of root systems, which are quite elementary. So, for example, the faucet delta plus. So when I choose a base, then I can speak of the positive roots with that fixed base. Sometimes I'm going to vary the base, but when the base is fixed, I can look at elements in roots, and with the fixed base, I say that beta prime is less than beta double prime if beta double prime minus beta prime is non-negative combination of non-negative integer combination of simple roots. So this is the most natural base. Then the properties of this faucet are that first, beta less than beta prime, any two roots that one is lower than the other one can be connected by a chain of simple roots. They exist. Beta prime equal beta 1, beta 2, beta s, which is beta double prime, such that beta I plus 1 minus beta I is a simple root. So I can keep growing with simple roots. Second, there is a unique maximal with respect to this order root. It is called the highest root. And the important thing is I'm assuming my root system is irreducible. If the root system is irreducible, I'll have a maximum in each of the components, and they are not real. Related to this is for any beta. See, I can decompose beta into combination of simple roots. The support of beta are these simple roots. No, I'm not going to do this. No. Okay, the last thing that I want to say here is that delta plus is the lattice order number of lattice. And in fact, the formula for the mean of beta prime and beta double prime is very simple. The mean of beta prime and beta double prime is the sum of the minimum C alpha prime, C alpha double prime, alpha, and sigma, where beta prime is the sum of C alpha prime, alpha, and sigma prime, sigma, and beta the double prime. So to find the largest element, smaller than both beta prime and beta double prime, what we need to do is just decompose each of beta prime and beta double prime and take the smaller beta coefficient. And it's important here that 0 is contained. So if have no, if their supports have no intersection, then the mean will be 0. Obviously, the formula for the join is not with the maximum, but from order theory, you know, if you have a mid, then you have then you have a joint, and there is. But so this is the nice lattice that we get, and the last thing is the classification. Classification. So let delta be a root system, be reducible to root system. Sigma be a base. Then the by law I'm required to call it Coxford Unity diagram. And creator not being able to refer to Faraday cannot drop the Coxford name. Is obtained in the following way. This is a graph with vertices sigma, the elements of sigma, and edges sigma. So either there are no edges with alpha if you talk about beta. So I consider the rank 2 system generated by alpha and beta. If it is A1 plus A1, I put no edge. A2, I put one edge. In all other cases, I put one edge. In A2, it's not labeled. In B2, it is labeled by 1, 2. And in G2, it is labeled by 1, 3. So the classification theorem then is and it is actually not, it is beautiful theorem. The proof is very nice, but it is actually quite elementary. It's not too difficult to follow, just to make a lot of steps. The Coxford thinking diagram determines delta uniquely. All Coxford thinking diagrams are. And they come in 4 series. AL, which have just a string with simple links. BL, string with simple links, and the last one is short. So the label is 2-1. CL, The last one is long. DL they are still simple links, but at the end you have this branching. E678. So what I'm saying is, you start here, you have these six vertices, and then for 7 and 8, you add one or two more. F4, you have the branching here. Doesn't matter whether you call it 2, 1 or 1, 2. It's the same thing. And G2 doesn't matter whether you call it 1, 2, or 3. And I want to point out the amazing thing that I think somehow people, many people understand very well and they don't feel that they should stress it. But for me, after thinking about this, I realized that the depth of the theorem is not in the classification. The classification is beautiful. The depth of the theorem is the following. I'm taking this structure and building the base, and then I'm starting and saying, okay, I can see rank 1 subsystems. Rank 1 subsystems are very dumb. There is only one thing. I can see rank 2 subsystems. I can see rank 3 subsystems, and I can go on. And probably the more I see, the better I understand the animal that I'm looking at, right? Like that joke about the elephant. I touch here, I touch here, I touch it, etc. What this theorem says is once you see the rank 1 subsystems, which there is nothing to see, just how many there are, and you see the rank 2 subsystems, you've seen it all. This is the amazing fact that usually if we have such a structure, which is high-dimensional structure, and you are building a simplex, that all the dimensions would actually matter. And in order to get the whole picture, we have to go up and up and up. And the beautiful statement here is that no, all you need to know is the skeleton in rank 2. And I'll stop here. And next time I'll define this proposed generalization of fluid systems. And I'll show how amazingly, basically all the properties that I have written, they actually carry over.
Any questions for Ivan?
Yeah.
This joint, you say it's not given by the maximum.
Well, obviously, if the supports are joined, huh?
Is there a reasonable formula?
Yes, if you go to the negatives, then the maximum becomes minimum, something like that. Yeah, there is a way to see.
There is one that's sufficiently complicated derivation.
Yeah, I think, or yeah, I think.
Any further questions?
Yeah.
You have a similar classification during for complexity questions.
Complex, it is more complicated. There are many. There is a joke going on that for some period of his life, Coxter, every time you meet him, he will tell he's a paper with the classification of the complex reflections. And if you are brave enough to point out that he gave you that paper 3 months ago, you can say, no, that was incomplete. He is the complete one. So, yes, there is, but it's kind of by no means anything as beautiful as this one. And there are, some people are making some assumptions, depending, yeah, it's more, nowhere near.
Probably you have to go all the way.
Not only this, I think, there is also the question of up to what as more what classes, what international classes we get.
Any further questions? Let's thank Ivan for the wonderful lecture.
Dit moet jullie in de wedstrijd kijken.